In the previous videos, we've developed lots of different derivative rules, really powerful rules that took us a lot of algebra and some kind of interesting concepts to come up with. But these rules have given us the power to take the derivative of any polynomial that we want much easier than we were able to do before. That's awesome. That's great news. The bad news is that we want to be able to take the derivative of any function, not just any polynomial. And there's lots of functions out there that we've already encountered in this class that are not polynomials. For example, we've seen radical functions. In this video, I want to tackle radical functions. Not all radical functions, but radical functions in a very specific form. Things like the derivative of 1 over x. We know how to take the derivative of 1 over x. We can do this with the difference quotient, right? It's just the limit as h approaches 0 of f of x plus h, so in this case 1 over x plus h, minus f of x, 1 over x, divided by h. This h is the problematic h that we're trying to get rid of. In order to do that, we got to make it a fraction divided by a fraction and multiply by the reciprocal of the denominator. I won't go through all the steps since we've already done them so many times, but as a quick reminder, what we do is we multiply this fraction by x over x, and this fraction over here by x plus h over x plus h, and that would give us the common denominator up top that we're looking for. Since we have a common denominator up here in the top, we can subtract the fractions. We got x over x times x plus h minus x plus h over x times x plus h. And when you subtract fractions that have the same denominator, you just write the denominator a single time and you subtract their numerators. So I got x minus x plus h divided by x times x plus h all over this h down in the denominator. We distribute this negative sign, it becomes x minus x, which goes away, and it becomes negative h. So we got negative h over x times x plus h divided by h over 1. Instead of dividing fractions, we can multiply fractions. We get negative h divided by x times x plus h times 1 over h. The h's cancel out. That's great news. All we got to do is evaluate the limit as h approaches 0 of negative 1 over x times x plus h. An easy limit to evaluate because this is a function is continuous at h equals 0. So if we change all the h's into zeros, we get negative 1 over x squared. The derivative of 1 over x is negative 1 over x squared. That's great. It's a good fact to know, but it doesn't really work as a rule, right? That only answers one question. What we'd really like is a way to answer a whole bunch of questions that kind of sort of look like this. And that's what we're going to do with our next example. In the next example, we're asked to figure out the derivative of 1 over x to the n for any power n. Can we figure out that derivative just using the difference quotient and then look for some patterns? Absolutely we can. In fact, the steps that we'll do will look a lot like what we did up here. We'd say this is the limit as h approaches 0 of 1 over x plus h to the n power minus 1 over x to the n power divided by h. Again, we want a common denominator. Up here in the numerator, the way we'll do that is we'll multiply this side by x plus h to the n power on the top and the bottom. And we'll multiply this side by x to the n power on the top and the bottom. And now we got this common denominator. Great, things seem to be going well so far. Up in the top, I have x to the n times 1, in other words, x to the n, minus x plus h to the n power times this 1, all divided by the common denominator that I have here of x to the n times x plus h to the n power. That entire thing is divided by this h, which I can think of as h over 1. And if I don't want to divide by h over 1, I can multiply by 1 over h. It'd be great if I could cancel out this h right here because then I could evaluate the limit. Can I cancel out this h? Yeah. Do you see it? Probably not. But what we have here is very similar to what we had a couple videos ago when we developed our power rule, right? When we're looking at x to the 10th power is x plus h to the 10th minus x to the 10th divided by h. Look what we have down here. We almost have that x plus h to the 10th power, and we almost have that x to the 10th power, and we almost have that 1 over h. These are written in the wrong order. It should be this minus this. Instead, it's the other way around. And we have this extra term that wasn't there before, but we have a lot of the same pieces. In fact, if I rewrite things a little bit, I can change the order of subtraction up on the top by factoring out a negative. So I have the negative of x plus h to the n power minus x to the n power divided by this times this. Instead of putting that whole product in the denominator here, I'm just going to put the h over here, and I'm going to put the rest of it kind of off to the side, just so I can sort of focus on the part that I'm most interested in. What I have right here is my power rule. Because think about what would happen if we expanded x plus h to the n power. We'd need to pull out Pascal's triangle and look for the n row in Pascal's triangle, figure out all our different coefficients, but most of them wouldn't end up mattering. The first term would be x to the n, but that would cancel with this x to the n. I think those I circled in red maybe in the previous video. And then the second term would be the one that's important. It would be n times x to the n minus 1 times h. It would only have a single h, and that single h would cancel out with this single h, and when I evaluated the limit, that's the term that would survive. And then all the rest of the terms, I think I put a purple box around them, would have more than one h squared or h cubed or h to the fourth. So even when I canceled out one of those h's with this h, there'd still be at least one h remaining, so when I took the limit as h approached 0, they'd all go away. I still have this stuff over here to deal with, but this stuff over here works out really nicely when I take the limit as h approaches 0. I don't divide by 0. The only problematic h is this h, and I can cancel this h with the h that'll exist in every single term when I expand out this binomial. What I'm saying is, without getting too deep into the algebra, this limit is going to evaluate as negative for this negative sign, n times x to the n minus 1 for the power rule portion of this fraction right here, times whatever this thing evaluates to when I change all the h's into zeros. Let's see, 1 divided by x to the n times x to the n. In other words, x to the 2n power. The derivative of 1 over x to the n is this mess right here. Negative n times x to the n minus 1 divided by x to the 2n power. Ugh, that sucks. That's ugly. I'm never going to want to use this rule. That seems like a lot for me to memorize. Well, maybe I could simplify this thing a little bit. I got this negative n, and then I got x raised up to some power divided by x raised up to some power. So think like I got x to the third power divided by x to the seventh power. I can cancel a bunch of those x's, right? I can cancel 3 of these with 3 of these, and I'm left with 1 over x to the fourth power. When I have a quotient of exponents with the same base, I can just subtract the exponents. N minus 1 of the 2n x's that I have down in the bottom will cancel with the n minus 1 x's that I have up top, and it'll leave me with the 2n that I started out with minus the n minus 1 that I canceled out with the n minus 1 up on the top. Ugh, that's still ugly. Can I simplify that? Yeah, absolutely. Get rid of these parentheses by distributing the n. You got 2n minus n, in other words, 1n, plus 1, because when you take the negative and distribute it to a negative, it becomes positive. What I'm saying is this is negative n times 1 over x to the n plus 1 power. It's a little bit cleaner than what I see here. So I guess we could make it a rule. I guess we could say the derivative of 1 over x to the n is equal to negative n times 1 over x to the n plus 1 power. But that seems hard for me, the student, to remember. I feel like I'm going to confuse that with the power rule. Well, I got great news for you. Instead of attacking this problem in the form that it's written in, that is, instead of figuring out the derivative of 1 over x to the n power, we could think about this as the derivative of x to the negative n power. Because negative exponents mean take the reciprocal of, loosely speaking. So 1 over x to the n is the exact same as x to the negative n. Therefore, the derivative of 1 over x to the n would be the exact same as the derivative of x to the negative n power. Think about what would happen if we used our old familiar power rule on this expression. Right? Our power rule from a few videos ago told us that when we have the derivative of x raised up to an exponent, we take that exponent and bring it down in front, and then multiply that by 1 less than the exponent. So if I were trying to do that in this case, I'd take the exponent, which is negative n in this case, and bring it down in front, and then I'd multiply by x raised up to 1 less than negative n. What is 1 less than negative n? It's negative n minus 1. What I'm saying is if we could just use the power rule, this would be our answer. But look what happens when we rewrite this. This is negative n times x raised up to the negative n plus 1 power. Because if I took this negative and distributed it through, it would change the sign on both of these guys. And when I have this negative exponent, I can rewrite that as 1 over x to the n plus 1 power. Negative n plus 1 is the same as 1 over positive n plus 1 as my exponent. What I have written right here is the exact same as what I have written down here. You lost me. What point are you trying to make? The point that I'm trying to make is you don't need this as a new rule. You don't need this. You don't need a special rule for rational functions. Our power rule works just fine. If you're trying to figure out the derivative of 1 over x, don't use the difference quotient like we did here. And don't try to use some new rule that we'd come up with for rational functions. Instead, just rewrite this with negative exponents. What's the derivative of 1 over x? Well, 1 over x, if I write it with negative exponents, is the same as x to the negative 1 power. I can use my power rule on this. My power rule says anytime I'm taking the derivative of x raised up to a power, what I do is I take that power and bring it down in front, and then I raise x up to 1 less than that old power. So negative 1 minus 1, in other words, negative 2. The derivative of 1 over x is negative 1x to the negative 2 power. The standard is, if your question is given without negative exponents, it's a good idea to write your answer without negative exponents. So it's a good idea to rewrite this as negative 1 times 1 over x squared. Remember, x to the negative 2 is the same as 1 over x squared. What I have written right here is negative 1 over x squared, which is the exact same thing that I came up with way over here. The whole point of this video is, with some kind of clever algebra, we can prove that the power rule continues to hold even when we have negative exponents. And that's a huge leap, right? Because if you think about how we proved the power rule in the first place, we used this Pascal's triangle. We relied upon the fact that the exponent was a non-negative integer, because otherwise we can't get the expansion using Pascal's triangle. So really, when I wrote the power rule a few videos ago here, I should have said, oh, this is a great rule, but it only works if n is a non-negative integer. But I didn't write that because you don't need this clause right here. Even though we didn't prove the power rule when n is a negative integer, when we first came up with it, in this new video, we've just proven that the power rule continues to hold even if n is negative, which is really cool. Because not only does it make the power rule more powerful, it allows us to use it on a wider variety of functions, it cuts down on the number of rules that we'll have to memorize if our goal is to come up with derivatives for all functions out there. To see if that made sense, let me leave you with an example. What's the derivative of 2 over x cubed plus 1? Somebody asked you this question. Can you give them an answer? What you'd want to do is rewrite this problem. Think about this as the derivative of 2x to the negative third power plus 1. Our rules aren't conducive to this notation, but if you rewrite it in this notation, it fits our rules really nicely. From previous videos, we know that the derivative of a sum is just the sum of the derivatives. So I can say that this is the derivative of 2x to the negative third power plus the derivative of the number 1. And we also know that the derivative of a constant times a function is just the constant times the derivative of the function. So all we have to do is figure out the derivative of x to the negative third power and the derivative of 1, and we'll have our answer. The derivative of x to the negative third power, as we just figured out, is something we can use the power rule on, which is awesome. It's negative 3 times x to the negative fourth power. You bring the negative 3 down in front and you subtract 1 from the exponent. Negative 3 minus 1 more is negative 4. The derivative of 1, because 1 is just a constant, is 0. So the derivative of this function is just 2 times negative 3, in other words, negative 6, times x to the negative fourth power. This is a perfectly fine answer, but again, since the question didn't have negative exponents, it's not a horrible idea to write the answer so that it doesn't have negative exponents. So maybe you'd write it in a form like this or something similar. But I don't want to get too hung up on how you present your answer. The point that I want to make are either of these are the correct answer for the derivative of this function.